Hi, folks. Today we're going to talk about the classical applications of graph theory. Now, when it comes to graph theory, we know what a graph is, but there are a few examples of how we can apply it, which are a little bit more interesting. And so these are problems which did something unique, or problems with interesting history, or problems which gave new approaches to mathematics. And some of them are fairly recent. And so we're going to go through three such problems. We're going to talk about the Königsberg problem. We're going to talk about the museum problem, and we're going to do the four-color theorem. To begin with, let's talk about Eulerian graphs, and let's see if we can visit Königsberg for the last time. And so we all know this problem. In 1736, Euler presented this problem. Given Königsberg, Prussia, it has 7 bridges. Is it possible to cross all 7 bridges exactly once and either return to your starting location or return to some other area? Where would we need to start in either case? And so this was the problem which developed the idea of topology and graph theory. And so all of it comes to this one problem. And so in topology, the idea of homotopy came to be from the idea that we don't really care how big these islands are. We can shrink them down to a point and it does not matter. And then in making this a graph, we have said that we can connect these regions via the bridges. And so this is showing us the general structure of this region. And so the graph is obviously Hamiltonian, but is it Eulerian, semi-Eulerian, or neither? And so the question is it possible to begin somewhere on this graph, cross every single edge exactly once, and then return to your starting point? And that one's a little harder. So let's do an easier version to try and demonstrate what's going on and see if we can come up with some ideas to how we can solve it. And so consider this example. This is one most folks have sketched at some point or another. Is it possible to find an Eulerian or semi-Eulerian path? And if so, where do you start and end? And so consider this image. If you'd like, pause the video, see if you can figure it out. Where would you start? Where would you end? And how would you go across this entire graph? And it turns out there are many approaches, but you have to start and end at the bottom two. If you started anywhere else, you would not be able to do it. But if you start down in the bottom left, you could go diagonal, across, down, across, diagonal, up, down, down, and then we would end up at this bottom right-hand location. And so we know that this is semi-Eulerian. What makes it semi-Eulerian? What is so special about those bottom two spots? And we only have so many tools we can use to analyze these structures. And so let's look at these bottom two and see what's special about them. The big thing is they have an odd degree. And so the two vertices on the bottom have a degree of 3. Each of the other 3 has 2 or 4. And so in this case, we see 2 edges. In this case, we see 4 and 4, but the bottom 2 have 3. And so now let's see if we can apply some intuition. Whenever we go to a node, we then have to leave that node, which means that there's always going to be an even number of nodes or an even number of vertices for every intermediate point. Only at the beginning or the ending could we have an odd number. And if we have an odd number at the beginning or at the end, well, that tells us that we're not going to be returning to that point in the end. And so we've just figured out what Euler's theorem is. And so suppose that you have a finite connected graph. Well, it's going to be Eulerian if each vertex has even degree. And so in this case, right above, if all of these had been even, then it would have been Eulerian. We could have done a path which would go through every point and end back where you started. A finite connected graph is semi-Eulerian if it has at most 2 vertices of odd degree. In that case, you start at one of the odd degree vertices and end at the other. If a finite connected graph has more than two odd degree vertices, then it is not Eulerian or semi-Eulerian. So we cannot do that one. And so let's do a final trip to Königsberg. Looking at it, we have a degree of 5, a degree of 3, a degree of 3, and a degree of 3. In this case, it is impossible to create a path which crosses every bridge exactly once. And this was the math that Euler developed. The idea that we can take different sized regions and shrink them down, the idea that we can connect these different ideas, this developed very large branches of math. And it's really tragic that we don't see more of this in K-12, because this is the type of math which we can all understand without too much difficulty, and it's very applicable. So here's practice problems. Consider the 7 graphs to the right. Determine which are Eulerian, which are semi-Eulerian, and which are neither. If you'd like, pause the video and give it a shot. Here's our answers. And if you'd like, you can check them out with the first one. We have degree 3, degree 3, degree 3, degree 3, degree 4. There's more than 2 with degree or with odd degree, so it's non-Eulerian. This one right beneath it, I think that's actually our Königsberg graph. And so that one is also non-Eulerian. With these two, we've got a 3 here and a 3 here. We've got a 3 here and a 3 here, and everything else is even. And so they are each semi-Eulerian. And with these 3, looking at it, they are completely Eulerian. Every node in this top square is either going to have a degree of 2 or a degree of 4. With this one, every single one has a degree of 4. And with this one, everyone's either degree 2 or degree 4. And so those were our Eulerian and semi-Eulerian paths. Now let's change to a slightly different type of graph theory problem. This is called the museum problem, or sometimes called the art studio problem. Consider the floor plan for a museum given to the right. The museum wishes to put guards on its interior so that the entire museum is visible to the guards. And we will assume the guards can see 360 degrees. How many guards are needed? Well, this is a challenging problem. And unfortunately, there's not really a good solution in general. This problem dates back to the early 1970s, so it's fairly new in the math world. It's a difficult problem. There is no general solution that'll work for all museums. There are some interesting relationships and strategies that apply to other problems, though. And so in understanding the techniques of trying to solve this problem, we'll be able to develop some additional techniques to solve other problems. Generally, this problem is studied in computational geometry, as solutions require heavy computations. And so let's go through a couple examples first. The first thing, will the best answer always have the guard placed in a quarter, in a wall, or neither? And it turns out it really depends. Often the best solution is going to be on the corner, but sometimes the best answer is going to be on a wall or somewhere in the center of the region. In this case, it's pretty clear that having a guard in the center is going to be the best bet because they can see down every single one of those hallways. But every museum is going to be different. And so we would have to have, or sometimes it'll be in the corner and sometimes it'll be having them centered on the wall. Is it enough to place guards so that they can see all the walls? Well, no. If you look at this one, we have guards and they're able to see every single wall, but there's still a space in the center which is not visible to any of them. And so you have to make sure that you're seeing every single location in the museum. It's not enough to just focus on the walls. Here's a couple examples. If you want, you can try them out. How many guards would you need for each one of these? Well, it turns out for the first one, you would need 3 guards. For the second one, you would only need 2. Now the question becomes, how can we figure this out? There isn't a good general strategy, but what we do have is we do have some bounds. And so Fisk's bound is an upper bound for the number of guards you would need. In 1978, Stephen Fisk came up with a graph theory proof that for an n-sided polygon museum, so a museum with n walls, you would need at most n over 3 guards. While this result isn't a solution, it gives an upper bound on the number of guards needed. If we go up a few, we saw this one has a ton of walls, but it only needed 1 guard. And so this is really an upper bound. We know that the maximum we would ever need is n divided by 3. In order to prove Fisk's upper bound, we need one more tool, and that is triangulation. So given a simple polygon, well, a simple polygon is a closed shape that is constructible with a number of line segments, none of which intersect. So we can't have intersecting line segments. For the basic versions of the museum problem, we assume the floor plan is a simple polygon. Any polygon, which is a simple polygon, can be broken into a collection of triangles through a process called triangulation. When triangulating, the corners of each triangle need to touch a corner of the polygon. If the polygon has n sides, it will be triangulated with n minus 2 triangles. And so here I have 3 simple polygons, and I've triangulated them a couple of different ways. And so you can see in this first case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 different walls. And so we end up with 1, 2, 3, 4, 5, 6, 7 different triangles. And that's where this n minus 2 comes in. 9 walls, 7 triangles. Each of the triangles has corners which are touching the corners of the museum itself. And so this one down here would not be a triangulation because we would need an additional line segment here. For this one, this would not be a triangulation because you can see that there are line segments going outside of the polygon. And for this one, this would not be considered a triangulation because while we do have triangles, they're all touching some central point, which is not actually part of the walls of the museum. And so when we are doing this, we're just breaking down a region into a whole bunch of triangles, like this. And so to prove Fisk's upper bound, what we're going to do is we're going to start with whatever shape the museum is, and we're going to triangulate it. And so here we have a triangulation. We have that we've broken it into a number of different triangles. If you counted the number of walls and subtracted 2, you would get the number of triangles that we have here. The reason we triangulate the graph is any guard posted on a triangular shaped room is guaranteed to see everything in the room. And so if we have a guard anywhere within this triangle, including at the corners, they're guaranteed to see everything inside this triangle shaped room. Our second step is we're going to apply a vertex coloring. Essentially, we know that all of these rooms are triangulated now. And so on each triangle, we are just going to color them. And so here we have blue, red, and green. We are going to go throughout the entire region, and whenever we see an uncolored node, an uncolored vertex, we're going to color it with whatever the missing color is. And so we have green and red. So this one would have to be blue. This one then would have to be green. And we can see blue and green. And if this one's blue, then this one must be red. And if this one's green and this one's red, this one must be blue. We can go through and color every single vertex using this strategy. And so we have now colored every single vertex. Well, there's 3 different possible colorings. If we have n rooms, then we have, if we have n walls, then we also have n corners. And so if we look at the 3 colors, the most that we would have is n over 3 for a given color. And that comes from the pigeonhole principle, actually. And so at this point, if we select one of the colors, let's say red, and put a guard stationed at that location, we will have guaranteed that the entire museum is covered in guards. And so these red guards can see every single location in this museum. Since there's three colors, if we have n vertices, there will always be a color which appears at most n over 3 times. And if we look up here, we could actually count them out. We have 1, 2, 3, 4, 5, 6 blue. We have 1, 2, 3, 4, 5, 6 red. We have 1, 2, 3, 4, 5, 6, 7, 8 green. And so choosing blue or red, that's going to be the ones which are going to give us below n over 3. Now, that's the most that's required, but we could have museums which require less, and we've seen museums which only require a couple of guards. It is possible to construct museums which would require that n over 3. And this right here is a diabolical example of a museum. And so here we have a 24-sided museum, and it requires 8 guards in order to see all of the different regions. There is no general strategy to optimize for all museums, but that's where computers can come in and help a little bit. And so that was the museum problem. It gave us the idea of triangulation, and it also gave us the idea of applying a coloring to the nodes. We're going to use those ideas a little bit for our next one, which is the 4-color theorem. This one was a little controversial. And so, given a map, we often want to distinguish between different territories using different colors. How many colors are needed to color a map? In the example to the right, Canada is colored by 3 colors. Is it possible to be done in 2? I'll let you try and figure that one out. Can you color this map using only 2 colors? Give it a shot. Now, when we're defining a territory, for this exercise at least, we're going to be simplifying things by adding some restrictions. And so we will only consider countries or states that are completely connected. And so we won't have things which are separated by some other area. We will ignore water features, and so oceans, lakes, etc. We're not going to include those. And also, if countries or states meet at a point but do not share a boundary, they can be colored the same color. And so if we have 27 different states which are all meeting at the same point, that's okay. They don't share a boundary. With these rules, what is the maximum number of colors needed? As a hint, it's called the 4-color theorem. And so that should give a solution. But let's go through it. And so let's look at the example of the northeastern United States. Here we have graphed, or we have colored it using 6 different colors. Can we do fewer? We can. Here it is done with 5 different colors. Can we do it with fewer colors? We can. Here we have it with 4 different colors. Can it be done in fewer colors? In this case, we cannot. For some maps, you certainly can, but in this case, we cannot. And the reason is West Virginia. And so if we consider West Virginia, which is blue, and note that it has 5 states which are surrounding it. And so if we start here with red, and this with green, then red, then green, then we will have this new one, which can't be blue, but it can't be red, and it can't be green. And so when we oscillate around, we end up needing a new color. And that's where our 4th color is coming from. It turns out we can do this for abstract regions as well. And so if you look at this one, we have a square and it has 1, 2, 3, 4, 5, 6, 7 different states around it. Much like the West Virginia case, the central square is surrounded by an odd number of territories. Whenever this happens, your map is going to require 4 colors to graph it. And so if you ever have a state or country which has an odd number of territories going around it, you are going to be required to have 4 colors. And so the open question was, are we going to need 5 ever? And that's a hard one to answer. Before we do that, let's see if we can articulate this in the language of graph theory. And so to start, let's use a little topology by trying to restructure the states. And so in order to determine a proper coloring for a map, we use a little bit of topology and a little bit of graph theory. To begin with, it might be beneficial to clean up the map a bit. And so here is the map of the northeastern United States. You can see everything is dictated by rivers and mountain ranges and borders with other countries and states, and it's a mess. And so using the ideas from topology, we can reshape these to be whatever we want. And so we can shape them to be rectangles. And here we have this map here rewritten in terms of rectangles, or I guess not always rectangles, but at least a little bit more squared off regions. In the example to the right, can you name all of the states in block form? Can you tell me what all of these different states are? We'll leave that for later. Once we've done that, we can actually then go back and turn this into a graph. And so we have a clearer understanding of where all the boundaries are. And so we can now make all of the territories into vertices. That's what homotopy is, right? And so with homotopy, we can or basically take all of these different regions and demorph them or deform them into a single point. And then all of the boundaries we can represent with edges. And so we can show exactly how all of these things are connected to one another. Notice with this state, I think it's New York, it's kind of separating out 2 different sections. We have this section up here, we have this section down here. All of it is connected through New York. And so this makes it clearer how all of the states are actually connected to one another. Once we do that, we can do a coloring, just like we did with the museum problem. And so we can now apply a coloring, just like the museum problem. The key difference between this problem and the museum problem is that with the museum problem, we could guarantee 3 colors maximum because it was a triangulated polygon. This is not a triangulated polygon. And so we might not be able to. In this case, we can't guarantee a 3 coloring. And as you start going around, you'll notice that this state here, it's going to end up having to have a 4th color. It's the only one that requires a 4th color, though. And so this is our 4-color theorem. The idea that 4 is actually the most that you need. And this is the exact case where you would need that 4th color. And so it turns out for any given map, 4 is the maximum number. Some maps don't need 4, but no map needs more than 4. And the proof was actually very controversial. In the 1970s and 1980s, a pair of computer scientists used topology to demonstrate that all possible maps reduced to 1,834 different cases. What they did then is they just had a computer check all of these cases. And in the end, they found that you only needed 4 or fewer colors. And so using a little bit of topology and a little bit of graph theory, they were able to plug this information into a computer and get the answer. This was the first time a proof was really done by the computer. And that was kind of a changing point. I mean, we've always used some form of technology, be it an abacus for counting or slide rule or something. But this time we said, we're going to do an exhaustive proof. We're going to check all of these different cases, and we're just going to let the computer tell us if it works or it doesn't work. And so that was weird. It took a while for people to get on board with that style of proof. And so final thoughts. When you think of these 3 classical applications, they show the graph as something more than a set of vertices and edges. Graphs carry and organize information, particularly information related to how things are connected. They can help us understand the physical world and carry far more interesting information than colors. We will soon apply these structures to other more concrete situations. Again, when we think about graphs graphs are just about the most applicable thing in all of mathematics, because as soon as we start looking for how things are connected, that's graph theory. Graph theory is all about trying to form these connections, whether it's connecting people, connecting things, or connecting ideas. And so every single field is going to use graph theory in some way, shape, or form. And so the better you know graph theory, the better you're going to be able to understand all those other fields too. With that, I'll let you get to work exploring where you find graphs in the real world. Good luck, folks.